Hi there guys. Now today we're going to have a look at what we call recurrence relationships. Just change this colour to something a little bit nicer. Or a recurrence formula. So if we take a look at this sequence, like before, we can say it adds 2, and we could even say the nth term of this, 2n plus 5. But we can also write it like this. So using that new terminology, so we're saying the second term, this 2, is the first term plus 2. That works, doesn't it? And then we could go on and list it. So the third term is the second term plus 2. And so on. Or, like I just said, the 2n plus 5 is the nth term. So this is what we mean by a recurrence relationship, this bit on the left. Now, you might think, well, what's the point? Because we've already got the nth term. But sometimes, in some sequences that you'll see, the nth term is actually quite complicated to use. So this allows us to express the sequence in another form. So let's take a look at some. So to generalize it, what we're going to say is the UK plus 1, that basically means the k plus 1th term, and I'm going to explain it slightly differently in a minute, is the kth term there, plus 2. Now, we change it quite often from n to k, and I quite like that because it kind of separates my nth terms with my recurrence relationships. Now in your books it'll probably swap between k and n willy-nilly whenever they want to, but I quite like to use k for this and n for nth term. It just separates everything up. So let's say k is 1. What you'd actually have here on this bit here, if k is 1, it'd be u1. And if k was 1, if k is 1 here, it has to be 1 here, and this would actually give me u2. So it's just saying what we did before, so u2 would be u1 add 2. If k was 2, we'd have 3 and 2. So it's just a way of expressing the next term. Okay, but that rule there would be exactly the same for that top one up here, but it would also be the same for that previous term add 2 and this one. In fact, an infinite amount of sequences. So what we have to do, with these recurrence formulas, we always have to state what u1 is equal to. So we normally do this with comma, and then stating what u1 is, like so. Alright, so let's have a go. So find the first 4 terms of this sequence here, which means the next term along is basically the previous term, add 3. And u1 is 8, so we've already got 8, so the first 4 terms we actually, in fact, only need 3. So let's think about getting the second term. What number would we have to put in here? It's 1, isn't it? Because 1 add 1 is 2. So when k is 1, this is the most important part of your working here. So k is 1, that's going to be u2. If k is 1, that's going to be u1 plus 3. So to find out u2, we need u1, and we're given that always. So 8 plus 3 is 11. So now we need the third term, so you just follow it along now. So if k is 2, we're going to have u3 equals u2 plus 3. Just pop in the k as 2 into these values in your formula. Now u2 we've had as 11, so u3 is 11 plus 3, which is 14. And you just do it again. So if k is 3, u4 is equal to u3 plus 3. Sub the numbers in and pop it down. Okay, not too bad. So you can go ahead and practice those if you need to and pause this, or just keep watching and practice it all together. It's completely up to you. Alright, this one looks worse. Now you'll notice that this is different, this bit here. And also, we're not just giving u1, we're also giving u2. And we want the first 4 terms. So we've got 3 and 4, we just need to work out the third and the fourth term. So let's think about making it the third term. What number has to go in here to make it the third term? Well, isn't it? That's, oh, sorry, I didn't mean to do that. That's 1. So when k is 1, and normally you're just using k as 1, you're going to get u3, because 1 plus 2 is 3. Now it says 2 uk plus 1, so if k is 1, that's 2, so 2 u2s, and k is 1, so u1. Do we know these? Yes, we do. 2 u2s, so if u2 is 4, 2 of those is going to be 8 plus 3, which is 11. Very simple. Now, personally, actually, I made this with 2 times 4. I wouldn't normally do that. I just go, well, just 8 plus 3. I just do that in my head. This bit here, just do that in your head. It's easier. Okay, so the next one, if k is 2, that's the most important part to write down. You must not skip this stage. So 2 U3s, well, U3 is 11, so 2 11s is 22. Plus U2, we get from the question, 22 plus 4 is 26. Looks more complicated. It really isn't any different than your basic substitution from your first or second years. Right, that looks way scarier though, doesn't it? So, a sequence of terms un, where k is greater than or equal to 1. Alright, so we're not putting any minus numbers in. It's just basically what we're used to. K is 1 or k is 2, k is 3. They're telling us it's a recurrence relationship. It's nice of them, but you can see that. This kind of gives it away with all this new terminology. And p is a constant. So before where we had a number here, it's telling us that it is a number. That's what constant means, remember? And it's telling us u1 and u3. So find an expression in terms of p. So that wording you should be very familiar with by now. So it has to have p in our answer. So let's just go with it and see what happens. So if k is 1, because remember we want u3, and we need to put a 1 in there to make u3. So if k is 1, we're going to have u3 equals p u2 plus u1. Just put in the 1 where you see a k up in this top formula here. Okay, so let's see if we can fill some more in. So do we know u2? Well, yes we do. That's 4. And do we know u1? That's 3. So we can say it's 4p plus 3 just by putting the numbers in. So is this an expression, 4p plus 3? Yes it is. Has it got a p in it? Yes it is. Yes it has, sorry. So this is an expression, that's an expression for u3 in terms of p. Then it probably asks you for u4 as well, something like this. So to make u4, k has to be 2 this time. Now, this is where it gets harder, because it's p lots of u3, and now you'll see that u3 isn't a number. So it's p lots of this. So let's pop the p on the outside, that's how we're used to it. Expand the brackets, and there you go. Okay, so that's again an expression, it has p in it. Now to go any further, what they're going to need to do is give you a bit more information. So for example, if they say that u4 is 14, well you've got an expression, no I don't. You've got an expression for u4, and you know that u4 is also equal to 14. So they're equal to each other. Then you've got a quadratic equation, you should know that everything needs to be on one side. And then you need to think about factorizing it to solve it. Now, I'm going to just skip to that stage because this video is not on how to factorize. You can pause it, try it, make sure that you're happy with that basically. And if you solve it, again, it's not part of this video, and you should be pretty handy at that. I personally, now, I hate decimals. I don't know why I've put this as a decimal, but I would be writing 5 over 4 here. So I'm going to add that in because I much prefer fractions. Okay, so they are the possible values of p. Okay, so that's it. That's really the hardest example that I could find. So get practicing your recurrence relationships. And we're not going to do that next. I'm going to show you some really tricky ones actually in the next video, but I want to make a separate video on them, and it's called -1 to the power of n, and you'll see exactly what I mean then. So tune in.